presentation in Unit 2 entitled They See Me Rollin. They See Me Rollin' on My Segway by Weird Al Yankovic. So, the goals for this particular presentation are that students be able to apply Newton's first law of motion to free body diagrams, and they be able to differentiate between mass and weight. So here's what we already know. We already know that force is a push or pull on an object, and that a force can change the motion of an object. There are lots of forces like gravity, friction, electric. There's a whole bunch of forces that we haven't talked about yet, but there are a lot of different types of forces. Now here's what we learned in the lab. We learned that a ball bearing will roll along a tile floor for a long way. So a very smooth ball rolls along the floor for a long time. The same ball bearing does not go nearly as far on carpet, or if you use a tennis ball instead of a ball bearing, it doesn't go nearly as far. Now, Aristotle's laws of motion are now incorrect. So you see this big X right here. They're wrong. But historically, people have always thought that objects seek what is called their natural place. And that's natural motion. Natural motion says, hey, this rock really wants to be on the ground. So if I pick the rock up in the air, it's going to do anything it can to go down because it wants to be on the ground. And they also said that objects, in order to take an object away from its natural place, required what was called violent motion. Now, the key part of Aristotle's law of motion says that any time that you push an object more, it will go faster. And that seems to make a lot of intuitive sense. But when you allowed the marble to roll along the floor, you weren't pushing it anymore, but it was still maintaining the same speed. So if there's no push, how is it moving? And so Aristotle would say that there is a force that's acting on the ball, and that's now considered to be incorrect. Newton came by, and Newton has the unit of force named after him because he's very, very famous for making lots of significant contributions to physics. A famous quote by Newton says, "If I have seen further, it's by standing on the shoulders of giants." He made significant contributions to optics. He was the first one to kind of split white light with the prism. He developed the laws of motion that we're going to talk about. He developed the law of universal gravitation, which we will talk about. He also invented calculus at the same time as a German mathematician named Leibniz, and he made significant contributions to fluid mechanics, which are used in lots of machines in order to raise cars using hydraulic lifts and those sorts of things. So, mass. Mass is a measurement of inertia or a resistance to the change in motion. Generally, it's referred to as the amount of stuff that an object has, the amount of matter. So how much matter is there will prevent an object from moving. Now, the standard unit of mass is the kilogram. Okay, it's not the gram. It's the only standard unit that actually has a prefix in front of it. Now, in the chemistry, we tend to use grams because grams is very, very small and useful in chemistry. But the standard unit is the kilogram. Now, weight is different. Mass and weight are often used interchangeably, but they're very, very, very different. Or they're not very different, but they're not the same thing. Weight is another name for the gravitational force. Now, weight and mass are synonymous on Earth because we're used to having a standardized gravitational field. You can't go anywhere on Earth and have gravity be significantly different than where you are right now. But because gravity depends on the mass of both objects, the Earth is so huge that there's not a significant difference depending on where you are. Now, weight is measured in newtons and tends to be measured with a spring scale. Okay, mass, on the other hand, is measured with a triple beam balance and is measured in kilograms. So they're two different quantities. Now, Newton's law of inertia part 1 says an object at rest will stay at rest unless acted on by a net external force. So now think about that. If you see a ball sitting on the table, that ball will remain motionless forever unless an external force acts on that particular ball. And somebody says, well, I can actually pick up the table. Whenever I pick up the table, the ball will move. Yes, because you've actually changed the balance of these particular forces. At that point, there would be a net external force acting on the ball, and therefore you've held Newton's first law to be true. Now, an object at rest will stay at rest unless acted on by a net external force. Now, another part of that is it's got to be a net force, because if somebody comes and pushes this ball with 10 newtons and somebody pushes the ball on the other side with 10 newtons, the ball's still not going to go anywhere. So this is an example of Newton's first law of motion. Newton's second law, or first law of motion, the second part says an object in motion will stay in motion unless acted on by a net external force. And we saw this in the lab. When you take the ramp and the ball and you allow it to roll, it continues to roll a long distance unless there's an external force acting on that. Now, you did see there was an external force acting on the ball whenever you had a tennis ball or it was on a different surface because there was what we call friction. Okay, friction is a net external force. It can slow the ball down. Now, if there was no friction, if you had this on something like ice, it would continue to go forever. Now, if we look at our first question, it says, put Newton's law of inertia into your own words and provide an example. The one that I like to use is that it's the law of laziness. Okay, lazy. We'll just, instead of laziness, we'll just call it lazy. It's the lazy law. It's the one in which objects don't like to change the way they are. They like to stay stagnant the way they are. They like to stay in bed, and when they're out in bed and doing things and moving, they like to keep doing that as well. Okay. Developing A2, it says, which object has a greater inertia, a car or a cruise ship? Remember, inertia is related to mass. It has nothing to do with velocity whatsoever. So if you were to look at this and say, hey, which one has the greatest mass, it's very clearly the cruise ship. You can fit many, many cars inside of this particular cruise ship. Next, it says NASA is investigating a round-trip mission to Mars. Describe the use of fuel on the trip. So remember, the law of inertia says that objects in motion will stay in motion. So the nice thing about inertia is once you get a space probe on its way, looks like a seahorse kind of, okay, once you get that space probe on the way to Mars, you no longer have to use any fuel. You can just cut the engines off. It's not very much like your car. In your car, if you cut the engine off, you're going to slow to a stop because on Earth and on the road you have friction. Well, in space, there's not any friction. So there's no net external forces. So all you have to do is point the space probe at Mars, shoot it, cut the engines off. Now, if you don't restart the engines before you get there, the probe's going to slam into Mars, and that's not going to work. So instead, you only have to turn the engines on in order to slow it down, or if you want to change course. Okay, those are the only ways that you have to change course. It's not an E, it's a C. Okay, so if you want to change course. Next, it says a rock is attached to a string and swung in a circle, as shown below. What direction will the rock fly if the rope is suddenly cut? So if you were to take this thing and cut this rope, you're going to say, okay, which direction is it going to go? And in order to know that, what you need to know is what is the velocity at this particular point. Now, I don't know if you have any experience with these, but this used to be kind of a toy that people would take, they swing it over their heads and then let it go, and it's really hard to kind of judge where to hit it because the velocity is actually moving what we call tangent to the circular path. So a tangent line is one that only touches in one place. So the rock is actually at this point moving in this direction right here, tangent to the circular path. So if you were to cut the rope right there, there are no forces that are acting on the rock. The rock will continue to move in the direction that its velocity is at that particular point. So this is really useful whenever you're spinning this thing in a circle. Let's say that you wanted to hit this point right here. Well, in order to hit that point right there, it would travel in a straight line from wherever you let it go. So you would actually have to let go right there in order to hit this target right here. Next, free body diagrams revisited. It says free body diagrams illustrate all of the forces acting on an object. We've already calculated the net force, and we've talked about how equilibrium is where the net force is zero. And we said that objects can have zero net force and still be moving. Because remember, if it has zero net force, that just means that it's got no acceleration, but it could still be moving at a constant velocity. So, fundamental B1, draw a free body diagram for a box in equilibrium. Okay, so if we do that, this is from the previous one, we could say, okay, there's a gravitational force, there's a normal force, those two things are equal, so I'm in equilibrium. Okay, the next one, it says a car is driving down the road at a constant velocity, draw and label a free body diagram for the car. Okay, so now we know it's moving at a constant velocity. Constant velocity means no acceleration, which means equilibrium. So in this particular case, the car is going to the left. So I'm going to draw my gravitational force. I'm going to draw my normal force. I'm going to draw my applied force. And in this case, the frictional force has to be the same as the applied force. Now in this particular case, some people may not try and draw it where it doesn't have an applied force or a frictional force. That's not true, because in this case you have to have the applied force of the car to make it move, otherwise it won't move at all. Next we have a box has 1,000 newtons of total force acting on it, resulting in a net force of 0. Draw and label a free body diagram for the box and describe its motion. Okay, so the first thing we want to say is the net force is 0. So that means the object has to be moving at constant velocity, or it can be at rest, depending on how you draw the free body diagram. Now, in order for it to have a net force of 0, the up force and the down force have to cancel each other out. The right force and the left force have to cancel each other out. So there's lots of different ways for you to do this. I'm going to go ahead and say 100 newtons to the left and 100 newtons to the right. Now, those two cancel each other out, and I'm still in equilibrium. But instead of 1,000 newtons, I've taken 1,000 and I've subtracted 200 from the total. So I've got 800 newtons left, which means I will have 400 newtons down and 400 newtons up. In this particular case, I would say that the object is either in constant velocity or at rest, depending on how those forces are acting. Okay, the last one says the sign below is at rest. Draw and label the other forces necessary. So if you were to look right here, you would see there's a 500 Newton force, but at this point it's acting at an angle. It's actually coming up and to the left. So in order for me to figure this out, I need a force to the right, and I need a force down to cancel out these forces right here. In order to figure out what those values are, though, I need to be able to use sines and cosines. Now remember from geometry, or remember from math, that you have this angle right here, and there's a relationship between this called the hypotenuse, and this is the opposite side, and this is the adjacent side. Now, whenever you do what's called the cosine, which is COS, the cosine of an angle is equal to the adjacent side over the hypotenuse. So if I'm trying to solve for the leftward force, I could say 500 times the cosine of 30. When I do that, I get the leftward force. The leftward force in this case is 433 newtons to the left. Well, in order to cancel that out, I need a 433 newton force to the right. Okay, the last one, I also need to figure out the force down is. 500 newtons, if I'm trying to figure out what the opposite side is, instead of using cosine, I would use the sine. Well, the sine of the angle is equal to the opposite side over the hypotenuse. So 500 times the sine of the angle, which in our case is 30, would equal 250. So that means there's a 250 Newton force up. Well, if there's a 250 Newton force up, there must be a 250 Newton force moving down. So our two answers are, in order to balance out the sign, you have to have a 250 Newton force down, which is probably from the gravitational force of the sign itself, and you have to have a 433 Newton force right, which means you'd have to have a second support kind of pulling the sign to the right.